Çetin has been area chair and technical program co-chair in many international conferences on signal processing and pattern recognition. He is also a member of the most famous associations and societies in this area of research and has received many national and international awards in recognition of his work. Now I have the pleasure to invite him to deliver his speech on brain computer interfaces.
Thank you, Begüm. Begüm, and thank you, Christina, for setting this up. I think it's a great seminar series. I'm very pleased to be here. So the talk will be on brain-computer interfaces. Before I actually start the talk, I'll show you a video. I'll tell you what this is, but this is sort of one of our first implementations of the brain-computer interface, and my student was very excited at the time. Posted these videos on the web, so you'll see it, and then later in the talk you will have an idea of what this is about and how this is done. Did you figure out what was going on? No? Start questions. Figure out what was going on. So basically, this was a brain-computer interface. The person was typing by thinking about certain things. We'll figure out what those are, but he was typing Sabancı Üniversitesi on the screen, but not all the letters were correct, as you see. There's some errors, etc. Pretty much the person was writing by typing. So today we'll hopefully get some idea of how this is done. So before getting into that, so let me give you an introduction of my research group. So I'm leading the Signal Processing and Information Systems Lab. Here in my group, there are currently 12 graduate students, 6 PhD, and 6 master's students. We also have a visiting faculty member this year from the US. There's a postdoctoral associate. We also have undergraduate students in our group, so if you're interested in doing research in these areas, we always welcome your participation as well. So this is my research group. In terms of the research that's carried out in the group, brain-computer interfaces is one piece, but there are other things. We work on computational imaging problem, as in biomedical imaging or radar imaging. We work on image analysis problems, again, medical images, microscopic images, etc. And then sort of half of my group currently works on some aspect of brain-computer interfaces. In general, we work on problems in which we collect some data through some sensors, and from that data we are trying to develop algorithms to extract some kind of information from data measures. So that's sort of the common theme of all of this research. But today, we'll pretty much just work on brain-computer interfaces. So let me start with this picture. So what do you think this picture might have anything to do with brain-computer interfaces? Well, go ahead.
Feedback.
Sure, yeah, but well, I have sort of, what do you mean by feedback? So basically a picture shown.
They get something on their head.
Sure, well that's interesting, but there's a more direct association. If you remember the kinds of things that were going on last summer, there is this campaign, you would remember? What was? Okay, that's the Ice Bucket Challenge, right? That's the ALS Ice Bucket Challenge. That was a popular theme in the news. And the point of the challenge was to raise awareness for the disease ALS. What's ALS? It's amyotrophic lateral sclerosis. So this disease is one of the primary motivators of brain-computer interfaces. So what's this disease? Stephen Hawking has this disease. So basically it's a motor neuron disease. It basically starts gradually. The person loses control of muscles starting with extremities, hands, arms, etc. And then this goes on through the body. At the end, the person cannot speak, cannot control any muscle. However, people usually live in this state for years, 5 years, 6 years, etc., or more, even more. So the mental activity of the subject is usually intact. So in this state, the unfortunate thing is that these individuals cannot communicate with the environment because they cannot use the usual output mechanisms we use, output channels, hands, arms, muscles, gestures, speech, any of those. So the point is to have these people active in their life. You want to have them communicate with the environment. And then one idea would be to use their brain signals directly, electrical activity of the brain, to understand what they are trying to tell, essentially. There are other diseases that cause similar issues with muscle control. So the idea, overall idea is, if you can, so the idea again is that since we cannot use the usual output channels, let's bypass those channels and use actually the source, the electrical activity from the brain, directly to the feed that directly to the computer. Of course, you have to be able to first measure such signals, and then you have to do intelligent signal processing and machine learning to make sense of what those signals are, and then you can use these in some application. You may have the person type, use a prosthetic device, use a wheelchair, or move a cursor on the screen. So that's the overall idea. Now there are details on these diseases which I won't spend much time on, but ALS is one of the primary motivators. As I mentioned, Stephen Hawking is one person who has this one, famous characters. Another one is Bulgarian, a famous baseball player in the US. Actually, in the US, ALS is also known as Bulgarian's disease, after his name. So there are other diseases. For us, the primary point of interest is that in many of these diseases, mental activity is pretty much intact. However, the person cannot use their muscles, hands, arms, etc. So again, so basically that's one of the primary motivators. So we want to come up with a way to measure brain signals and how people communicate. So you can, this is sort of a list of potential applications of brain-computer interfaces. This is the first one I mentioned. So for these disabled individuals, you want to have them communicate with the environment, type, etc. Do environment control, maybe turn on the lights or whatever, things like that. And possibly movement restoration. Maybe you can come up with some kind of neuroprosthetic device to have them move what looks like their arm. Another thing, of course, is that you may have them use devices such as wheelchairs, vehicles, robots, etc. So this is primarily for people with disabilities. But as BCI technology has developed, people have started thinking about other application possibilities for healthy individuals as well. So after all, it's a communication channel. Currently we communicate with the environment using our usual tools, but what if the idea of using an additional channel directly from the brain, one more channel? And that's one place where this has been exploited, or people are starting to exploit it, is computer games. So there you pretty much use everything you can. Why not add one more thing to dominate the world or whatever you want to do? So that's another application area. Another application area for healthy individuals is to monitor the brain activities of operators in critical tasks such as long-distance drivers, pilots, air traffic controllers, and somehow get some information about their brain activity, such as whether they are tired or not, or things like that, and use that in real time to send out alerts, etc. So that's another potential application domain. So yet another application domain is to use the brain signals in certain therapies, such as therapy of stroke, as I will mention later in the talk. So this is not for communication, but use the brain signals somehow to help the process of recovery of a patient from some kind of disease. So we'll revisit some of these throughout the talk. So back to this picture. So this is essentially what we want to do. So the work of my group, of course, I mean, we implement these systems, use them, but in terms of academic work, most of our research is here to develop new signal processing and machine learning techniques, and I'll talk about that. But before we get there, we have to understand first of all, how do we measure brain signals? So let me give you a picture of how this is done. So there are different types of brain-computer interfaces with different levels of invasiveness. At one extreme, there are very invasive techniques in which we put in electrodes to the inside the cortex of the brain in gray matter. Of course, this is done only with a small number of patients when this is justified, not useful for a very great number of people who might use BCIs in the general population. There are techniques that are called sort of partially invasive. So in this case, the electrodes are on the inside the skull, but on the surface of the brain, on the cortex. So these are called partially invasive. And then on this extreme, there are non-invasive techniques. This doesn't require any surgery. You just try to measure brain signals from outside the brain, outside the skull. So we are mostly interested in these types of techniques for their practical potential, but we also look at signals in these types of interfaces out of interest. So let me go through this listing, starting from invasive techniques. Here's an application of an invasive brain-computer interface. There is this brain-computer interface called BrainGate. This is a consortium. Part of it is at MIT, part or MGH, Mass General Hospital in Boston. Part of it is at Brown and Stanford, etc. So here, you basically do neurosurgery to get into the cortex. They have these pin-type electrodes. Essentially, they go into the gray matter of the brain. So, of course, the nice thing about this is that, well, you measure very high-quality signals, pretty much at the level of single neuron firing. You can detect such signals. Of course, they are invasive, hard to use for any patient, and also there's sort of long-term effects of, I mean, their scar tissue buildup, etc., and using them for a very long time could be tough. Although, in the website of this consortium, they actually talk about a patient using such a device for something like 1,000 days. Yeah, so they are really trying hard on this. So on one extreme of this, there are also people are developing different interesting sensor technologies, and when they develop these, usually they first test them on animals, and then testing them on humans take care, of course, a very long development cycle. So that's at one extreme, invasive BCIs. This is a picture of a person using this kind of brain-computer interface. Okay, second is partially invasive brain-computer interfaces. So here, what is done is that, again, you go into the skull. There's part, I mean, but somehow they call it, to me, it sounds very invasive, but from a medical point of view, they call this partially invasive. Still, you open up the skull. But the thing is that you don't go into the gray matter of the brain. So you put the electrodes on the surface of the cortex. So it's not, I guess, as bad as the electrodes in the first case. So this is called electrocorticography. So this is sort of a cartoon picture of a grid. I'll show you a real picture later that has blood and things like that, so I'm not showing you here at this point. It's too early. So basically from this, you cannot get single neuron firing type activity, but you can differentiate things like, well, which finger the person is trying to move, things like that, and I'll give you an example of that from our work later. Okay, and then going towards non-invasive brain-computer interfaces, this is the sort of the widest area of research and activity. There are different ways you can try to measure brain's activity from outside. The one that we'll talk about most is electroencephalography. That is the most promising one for brain-computer interfaces for a number of reasons. But there are these others. So fundamentally, what we want to measure here is the electrical activity of the brain. So neurons have basically synaptic activity through which there are some ionic currents in the brain, and that creates electrical potentials, and you can measure them on the surface of the brain. So EEG tries to measure this directly. The others are sort of indirect ways to get to this information using, trying to detect magnetic fields, or as you will see here, information about the oxygen level of the blood, etc. So I'll give you quick pictures of these sensors, and then we'll spend most of our time on understanding EEG. So starting with these, so the first one is functional magnetic resonance imaging. MR imaging is, of course, something that we all know something about. So in this context, functional MR imaging essentially exploits changes in the magnetic properties of hemoglobin as it carries oxygen. So pretty much, if there is some activity in some part of the brain, the oxygen levels there increase, and through MRI, essentially, you are trying to detect that. So this modality, fMRI, provides very good spatial resolution. So basically, when you have a person do some kind of activity, you pretty much get a good picture of which part of the brain is active at that point. It doesn't give you very good temporal resolution. That is, as time goes on, how do these signals change? That's not that good. So that's one piece of basic information to keep in mind. And then, so MR, of course, works with radio waves. Another modality that tries to get to the same information using a different type of signal is functional near-infrared spectroscopy. So this uses infrared signals, trying to get to the same kind of information, blood oxygen levels. Again, this provides reasonable information about the activity in a certain spatial area. However, the temporal resolution is not that good. So some people have tried this, but it is nowhere near EEG currently in terms of its potential to be used in real-time brain-computer interfaces. Okay, magnetoencephalography tries to find the magnetic fields that are generated when there is synaptic activity, when neurons fire pretty much. This again gives you a good picture of the activity spatially. However, it's not something that you can really use in daily life. It's used in a clinical environment for certain tasks, but again, for the daily task of using for communication, this is currently not a practical modality. So this brings us to what we are mostly interested in, and we'll talk about, which is electroencephalography. So EEG was, I think, measured from animals in studies back to 1800s, late 1800s. And then the first time it was recorded from a human in the literature was accepted to be in 1924 by Hans Berger. And this is believed to be the EEG recording that he actually did. At the top here, you see a time series data of EEG that he has recorded. And at the bottom here is a sinusoid. To those of you who study sinusoidal signals in some place, will recognize it's the sinusoid at a frequency of 10 Hertz. So this is quite interesting. Actually, the first time we have set up our EEG system in our lab and connected it to a person and asked the person to sort of close his or her eyes and relax, and then we looked at the signal on the screen. It's pretty amazing. So those of you who are studying especially things like electrical engineering, etc., might have played with sort of function generators and looked at the data on an oscilloscope, sort of generate a sinusoid and see it. It's pretty much like that. So basically, this changes from person to person, but pretty much when you have a person relax, close eyes, and then look at the signal, you see the sinusoid at 10 hertz, a very nice signal in the, that's the background activity of the brain essentially. And we'll talk about how this is exploited, that frequency structure, etc. So what we measure here is from the surface of the brain, we measure some electrical activity. It's usually at the microvolt level, 10 to hundreds of microvolts, very, very weak signals. What we are recording is, well, there's sort of, as I said, there's ionic current flows among neurons, but we are measuring it on the surface. So we are not really recording activity at the level of single neurons or so. This is at the level of thousands of neurons firing together. So they should there should be an activity in which these thousands of neurons are synchronously firing. That's the kind of activity we detect through EEG. And they should have similar spatial orientation. And through EEG, the signals that you detect sort of more accurately are usually the ones that are closer to the surface of the brain, not very deep in the brain. So EEG has been in clinical use for a long time. So this is not brain-computer interface, but rather clinical use. It has been used in diagnosis and monitoring of epilepsy. It's used to study sleep disorders, etc. So that is well established in medicine. As opposed to modalities like fMRI, it provides low spatial resolution, right? So basically we have these electrodes put on different parts of the head, and then what happens is that there's brain activity inside somewhere, you are measuring it on the surface, signals get mixed up as they propagate through the brain. So the spatial resolution is not that high. You cannot pinpoint exactly where the activity is, but we have an idea of roughly which area of the brain the activity is at. However, it provides very good temporal resolution. So you record time series data pretty much in real time. You are figuring out whether the signals are getting stronger or weaker, etc. The greatest advantage is it's non-invasive. There is no harm to the patient. There is no signals or there is no surgery or anything. It's just passive electrodes. You are just listening to the person. The only discomfort, I suppose, is a small amount of gel that we might put in between the electrodes and your scalp, and that's pretty much it. It's easy to use. It's kind of relatively cheap. I mean, academic grade systems are still expensive, but their cheap systems are coming up. Measuring data is very, very cheap, so it has great potential for use. But what are the challenges to use this system in BCI? First, signal levels are very low. As I said, microvolt level, there's noise, so somehow you want to be able to extract information from such challenging signals. Second, the activity is deep somewhere in the brain. We are measuring on the surface, so there's physical propagation through the different tissues in the brain. So what you are measuring is not really what the actual activity is, but something that's related to that activity. And that one of the implications of that is that you don't get very good spatial resolution. The other thing, of course, is that, well, many things go on in the brain at the same time, and you are trying to measure one piece of information from it. So how do you get that information? So if you describe it this way, it sounds like a science fiction, so how's that possible? The key is what's mentioned, at least currently, where in terms of what the current state of the art is. We design BCI systems to extract sort of commands of the person from EEG data by designing these experiments. We don't just put the electrodes and listen and figure out what the person is thinking about, but rather we design an experiment in which we try to have the person generate certain types of pattern from which we can make sense of what the person is trying to do. So that's the key, exploit. And that means you have to exploit knowledge from neuroscience, what is known in neuroscience, to exploit these known and consistent patterns and responses of the brain. So I'll get back to this point in a minute. Any questions at this point? Any remarks? So this is the basic piece of information on EEG. Now, let me try to give you sort of a visual flavor of what these things are. So basically, we put electrodes on a cap. So I'll show you what the cap will look like anyway. So this is one of the caps we use in our lab. So you put it on the person's head, and then there's these locations for electrodes. There's an international system of standard of where you should put the electrode. That's called the 10-20 system. You sort of have a measurement from the nose to the back of the head, and then ear to ear, and then make some measurements and put electrodes at the right locations, and then each electrode measures activity just below it. You do it this way so that data sort of collected in different labs can be compared. So these are pictures of our system in our lab. This is one of our electrode caps, and then what you put into these caps are these electrodes. So this is a set of 32 electrodes. Sort of each electrode goes into one of these sort of holes, and then you put some gel between the electrode and the surface of the head that ensures conductance between the two. And then you measure the data from multiple channels of this form, which then goes into an amplifier and an A to D converter, as shown in here. So you measure the signals that goes in here, and then from here you feed them to a computer, and whatever processing you want to do, you do it on the computer, and then you show the results on the screen, just like I showed you at the start in this typing system. So those are the ingredients, physical ingredients of the system. So in our lab, we use brain-computer interfaces for two main objectives. One is for communication. As I mentioned, communication of patients is a core issue. And the other one is for rehabilitation of stroke patients, as I'll describe later in the book. So back to now this picture, this question of how do you design BCI systems to reliably extract comments from EEG? You have to exploit known and consistent patterns of the brain. So currently there are 3 or 4 such patterns that are well known from neuroscience and that are used reliably in brain-computer interfaces. The first early one of those is called slow cortical potentials. I'll not talk too much about this. That requires some training of the patients to change their brain rhythms. So currently it's not one of the most practically used ones, but these 3 are. I'll show you examples of the last 2 from our lab, but this one, we did some work here as well, but let me first mention what this is. This is quite interesting. This is called steady-state visually evoked potentials. So what happens is that when you show a person sort of a periodic pattern, let's say a visual pattern, some flickering light with some frequency, versus a different frequency, what we usually observe is that if you do this for sort of in a regular time interval, you look at the electrical activity of the brain, the oscillation that you get, you measure from the brain of the person, matches the frequency of the flickering light. It's quite interesting. And those of you who are studying sort of linear systems, linear time-invariant systems, will have some understanding of what this might look like. It's as if the brain is working like in a linear time-invariant system. You put in a sinusoid, you are measuring a sinusoid at the output. It's quite interesting. So you can use this as a brain-computer interface. So let's say you want to have a sort of keypad of your phone, there are the 10 digits, and then you can have each digit flickered with a different frequency.